today matter?
Thank you, Frans. My job is like this. But he says I must have a job. So first of all, welcome to everyone, but I first want to welcome people that we really are excited that they are here this morning. Professor Luiso, I only have Luiso. Thank you that you are here. Professor Luiso Nonkwa, he's the chairperson of the National Research Foundation of South Africa. We are really glad that you could make your way to be here. Professor Samuel Banda, he is the Acting Director, Biostatistics Medical Research Council. Thank you, Professor Banda. We really appreciate because we have now ties with MRC and the department with the Biostatistics Chair, and we are really appreciate that you are here. And then Professor Debora Nolan. I asked her who should introduce her. Professor Potgieter will have a quick introduction, and she will follow by introducing herself. Welcome here, and I do not have words to say thank you for your willingness to be here with us. In your tight schedule, because you are the chair of your Department of Statistics at the University of California, Berkeley, and I know that you have a very tight schedule. Thank you for that. And also, by the way, also say thank you for your husband that he accompanies you. Professor Maseko Lusahana. So this is our president-elect for SASA. Thank you for being here and make your also time to be here. We really appreciate that. And of course, our own Professor Marieke Potgieter. Thank you, Prof. Really, she's our Deputy Dean, Teaching and Learning of the Faculty of Natural and Agricultural Sciences. Thank you for being here. Thank you for opening this ceremony. I think this is also close to your heart because it is directly involved in the teaching program. So thank you for being here. Professor Steve Koch. Where's Professor Steve Koch? He was here. Thank you, Prof. You know, we are his servants. Prof, you are the head of the Department of Economics. Thank you for being here. And I always say, let us have a cup of coffee. Now, today is the first cup of coffee. There will be a series of cup of coffees. Right. Then, Mr. André Zitzke, thank you for being here. You are the manager, Global Academic Programs Africa of SAS. Although SAS and R is not, it is compatible, but, you know, we have to serve both. No, I mustn't say it. God. Thank you for being here. We really appreciate it. And then, of course, the people from the University of Limpopo. We are really glad that you are here. Thank you for your time because it is in the exam period. It's difficult, and we really appreciate that you are here. I think this is very important for the whole South Africa that we are together in this. And also the people from Saul Plaatjes University. Thank you for being here. And of course, the own staff of the department. This is for us a very exciting adventure. Welcome, and I hope that you enjoy the following days, but the opening ceremony. And as Frans announced, it is a video. It will be on the website of SASA as well as the Maths Association, because I think it is very important for all of us that we implement the new thinking in our undergraduate program. Thank you. And now it's Professor Marieke that will take over. Thank you.
Thank you very much, Professor Becker, for the kind introduction. I always enjoy spending time in this department. It's a department with lots of energy. You look around and I just could sense the vibe entering here. There are high expectations. And we are so happy to have Professor Nolan visiting us. What I could gather from the documentation is that this is an opportunity to teach the teachers, where Professor Nolan will be imparting her insights, her expertise, and sharing that with us so that we are equipped to teach and to walk in her shoes. This is a hands-on workshop on content and non-traditional skills that are needed to prepare students for advanced data analytics and data science. I saw that on the title of the first slide. This workshop is organized in recognition of the fact that the workplace is changing so rapidly. The world of work is undergoing a so-called fourth industrial revolution, and it is very hard for universities to keep up and to be leading from the front in terms of developing the knowledge and these non-traditional skills that will be required. In fact, I think we acknowledge that the best we can do is to at least launch our graduates properly and equip them with the mindset of lifelong learning, because reskilling is going to be the name of the game, and there's no way we can really equip our graduates for life. But in recognition for how much change is happening, what big data is doing, and computing power, this is the acknowledgement that we at least need to come together, figure out how to change our syllabi, what to teach, what not to teach, and how to develop the skills, at least for as far as we can see. I wish all departments would do the same. My own department, chemistry, we are very traditional in our thinking as to what constitutes the discipline of chemistry. But I sense in this environment a willingness to think out of the box, to embrace change, and to really engage with the challenges with the view of equipping students. And that I value so dearly. That you're not here today for your own benefit. You're here today to be enriched, to learn in order to train students better. You're willing to rethink the way that talent is developed and deployed. And what higher good could there be than to be able to have that opportunity? At a university like Pretoria, we really have the cream of the young people of South Africa enrolling at that institution. I know we don't always feel like that when we mark exam scripts. I realize that. But if you just think a bit about how many students actually can enroll for a study program that is maths-based. The whole country produces only about 10,000 students with maths at an appropriate level in high school, that they can be trained for the whole range of disciplines, from engineering through to health sciences. So we have a treasure in front of us every time we stand in front of a class. And I looked at the CV of Professor Nolan, and I'm convinced you could have no better person to lead you on this quest. Except for a few years as a young programmer at IBM, she has spent most of her professional life at UC Berkeley, University of California, Berkeley, and she's held numerous positions of leadership and management nationally. At the University of California, in her department, where she's currently the chair, as Professor said, of that department. I looked through the long list of appointments and volunteer assignments in her CV, and it struck me how many of those were focused on teaching and learning. It also struck me that a large number of them were focusing on equity and diversity, also very important for us in South Africa at this point. Just to name a few of those on teaching and learning, she's currently a member of the U.S. National Commission for Mathematics Instruction. That's countrywide in the United States, am I right? It's the end of a 3-year term. And the 3 years preceding that, she was the member of a working group to revise curriculum guidelines for undergraduate programs in statistical science. And this is a presidential initiative from the American Statistical Association. That's really right at the pinnacle of decision-making about curriculum design, about instruction, about teaching and learning. And she's clearly a very experienced teacher. She's taught courses at all undergraduate and postgraduate level and has developed a number of courses. I noticed during the past 2 years she developed a course on principles and techniques of data science and another one on communicating with data science. So we're looking forward to what you bring from those insights and expertise and to this workshop. I have to warn you, Professor Nolan, that this workshop is in a small window. Those lecturers sitting in front of you taught classes until yesterday. Exams start on Saturday. So these few days are in between. Not only are they exhausted from what they've done, they're quite anxious as to what the students will give back to them to show whether they were effective in teaching or not. You'll have to bear in mind that if they doze off, you need your special tricks today to keep them wide awake. But let me tell the participants something about what we expect of them. Maybe that'll keep them sharp. You know, we will expect you to walk in the shoes of Professor Nolan immediately afterwards. You know, the secret of teaching is to appear to have known all your life what you've learned yesterday. So this is your challenge for the workshop. And there's another thing just to keep in mind. There are 3 things to remember when teaching. Know your stuff, know whom you are stuffing, and then stuff them elegantly. With that, I open this workshop and I invite you to the podium. Thank you.
So a year ago, I was in Marrakesh, Morocco, and that's where I met Andriette. And I was giving a talk about data science and integrating computational thinking with statistical thinking and bringing more data science into the statistics curriculum. And that's when she invited me to come and come in a year and hold a workshop for teachers of statistics. I was really pleased to get the invitation, and I'm really happy to be here. And I want to start by giving you another introduction of myself so that you can see where I'm coming from when I talk to you about data science and computational thinking and statistical thinking. So my first encounter with statistics was in the 1970s as an undergraduate. I was a mathematics major. You couldn't major in statistics when I was an undergraduate at my college. And I got a summer internship working with Carolyn Bird. And she was writing a book about the changes in the United States in families as a result of women going into the workforce. And to get material for her book, she partnered with Women's Day magazine. And that was a weekly magazine, and they published a little survey in that magazine. The women who bought the magazine could tear out the page of the survey, fill it in, and mail it in. And my job was to analyze the data. Now, I had never had a statistics course before. I was a pure math major. I was into courses like real analysis and measure theory and things like that. So I was a little unsure about whether I could actually do that. One of my professors gave me a book and said, "It's all in here, you'll be fine." And that's when I found that that book was full of formulas, and I could sort of puzzle out, okay, this is the particular test that I think I should be applying, but not really having a clue as to what I was doing and feeling really uncomfortable about it all. And that convinced me that I never wanted to touch statistics again. But fortunately, I had yet another experience. And, oops, wrong direction. And that was working at IBM, as was mentioned. My first job after getting my degree as a mathematician was to become a programmer at IBM. And I was assigned to work with market researchers, and they had collected data from all over the world about their products, their IBM computers. And SAS then was a brand new software system. It was, I learned how to use it, and the market researchers said, here's our data, just give it to SAS and tell us what it says. And that was it. So that was my second introduction to statistics, where it's like, they thought that the computer program SAS just kind of knew how to analyze the data, and I was just kind of the monkey at the machine, basically, typing things in, punch cards, the whole works. And so those two experiences together led me to start taking night courses in statistics and got me really interested in how powerful statistics could be. And then I decided to go to grad school, and now I'm here. But those two things taught me that doing a good data analysis is not the same as a simple application of a formula out of a statistics textbook. It also taught me that doing a good data analysis was not simply punching running a few functions in a software system like SAS or R. That you needed more. That the hardest part about doing a good data analysis was understanding and figuring out what to do. And it's hard to teach that, and most of the courses, many of the courses that I was taking as a budding statistician were not teaching me those kinds of skills. So a little last bit about my background, that led me to really care about how we teach statistics. And so working with Andrew Gelman, we produced a book called Teaching Statistics, A Bag of Tricks, and that has lots of activities and demos that you can use to teach in your classroom. And so the idea was to move away from lecture-style teaching and to get students engaged through activities and demos. Another endeavor that I've gone through is working with teaching through case studies. Terry Speed and I published a book called Stat Labs, and it teaches mathematical statistics through case studies. So every chapter is it's a problem and a set of data to analyze, and then you learn the mathematical statistics you need to know to analyze that data through solving a particular problem. And then most recently, tying my experience in programming and computation back into statistics education is working with data science and case studies again to look at problem solving from both a statistical and a computational perspective. And that's my work with Duncan Temple Lang, a case studies approach to computational problem solving and reasoning with data. Okay, so teaching statistics today has come a long way from what I experienced 30, 40 years ago. But I'd still say that we've got lots of room for improvement. And at this point, we've already started with a very interactive session before the formal workshop opened. I'd like you to just, before I tell you my 8 or so big beefs with the way statistics is traditionally taught, I'd like you to just talk to one of your neighbors. You can turn around and meet someone you've not met before or whatever, and let's just take a minute to say, what do you see as problematic with the way statistics is taught? And then I'll tell you what I see as problematic. And hopefully we'll have some common ground. All right. I see there's a little bit of a lull in the conversation, maybe? So I'll run through what issues that I have, and I'll be full disclosure here. Some of the things that I'm complaining about are things that I have done and still do in my classes. So these are criticisms of myself as well as the way the teaching profession in statistics is in general. Okay, first one up is that we often reduce is that better or worse? That's better? Okay. Maybe I'll hold it like this. It's we often reduce what our statistical lessons are to sort of standard little catchphrases, and we present a problem with a very simple story and then say, and so what's wrong? And a lot of the times statisticians our responsibility is to say what's wrong with this, as not to, well, how do we work with this? How do we do this? So association versus causation, statistical significance is not the same as importance, and selection bias are just some of the kind of catchphrases which are really important, but too often we reduce statistics to these tiny little stories and then we can label them as what's wrong and not really know what to do. On the other hand, there's the serving students canned data, where we learn one method in the class, we teach them one method, we give them one data set that we have prepared for that one method, and they prepare one analysis. So essentially, they open the can, they heat it, and they serve it back to us. And there's no real context for, I've got to figure out, is this the right kind of analysis to be performing? What is the problem I'm trying to address? Another one is that if we're looking for data, we just collect data on our students. And all these things about selection bias and representative samples, that's all kind of, we ignore it while we collect data on our students. So rather than, we should work harder to use data that have some kind of representative sample or some sort of solving some kind of problem. Okay. The other one is the big data problem. You find some big data online. It's so big that it must be right? It must be whatever message or we can ascertain from that data set must be the right message. It's so big, it's nearly everybody, so it must be right. We'll be looking at that in a little more detail later in the workshop. The other is the sense that EDA and visualization are just something that you teach maybe for a week or two to first-year students, and then after that you don't bother with it. So I say that is EDA is for babies, and theory is for grown-ups, because that's what the real stuff is. Right? The normal curve. Normal theory is the center of all statistics. That's all we need to figure out is how do we get those p-values from the z-test or the t-test or whatever it is? And we rely solely on mathematics. Here's another one. Computing is, we don't integrate it into our classrooms. We leave it to our laboratories or discussion sections, and we let the students sort of pick it up on their own, or worst case, we give them a template of code where they just have to change the variable names and rerun the code, and then they've done their data analysis. And so we maybe review the bare minimum that they need at the beginning of every course, but the students don't have a sense of how to actually, on their own, carry out a data analysis. And this is a new one. It's about reproducibility. That's a very growing concern in science in general, and it's something that we can even begin to address in some ways at the introductory level. And so I say blink on reproducibility, meaning there's no sense of the stuff that you're doing now you'd ever have to look at again, you or anyone else. And no one needs to reproduce your results to show that they are in fact good results. Okay, so do any of those match what you guys came up with? Well, I'd say that's an issue with how statistics, even when it's taught at the before the university, it's often taught in that same sort of procedural algebraic way, and the subtleties of what am I doing and what does it mean, and are devoid of any kind of problems that the students are working on in statistics. So yeah, focusing on the procedure as opposed to the concept, and what is the problem I'm trying to solve, and how is this statistic that I'm computing solving that problem? So in particular, I want to focus on the idea of the statistical context and the computational context are important, and they need to be integrated better. It's like the the whole point, as Terry Speed said out of the ICOTS in 1986, is the whole point of statistics lies in the interplay between the context of the original question and the statistics that you're using to answer that question. On the other hand, there's this context should also include computational context, because the idea of having statistics centered on normal theory is an outdated context. Now that we have very powerful, fast computers, we can be solving problems using different techniques that take into account the computational context. So some suggestions for how we might want to change the way we teach is to provide open-ended problems with context for students to work on. Have them experience the full data analysis cycle that includes data cleaning, data wrangling, exploratory data analysis and visualization, and to not just leave EDA and visualization to something that you do at the beginning and then forget about that skill, but to include it throughout the entire data analysis process. To emphasize the core computational paradigms that are behind the language R, or it doesn't have to be the language R, but that's what we'll be talking about in this workshop, to emphasize the core computational paradigms so that when you are faced with a new problem, you have a sense of how to go about it, solving it from a computational point of view. To free statistical theory from normal theory, and then to employ ideas such as the test train paradigm, the full reporting of dead ends and effect sizes and data design, not just what's my p-value at the end of your analysis. Why do we want to do this? I strongly believe that if we bring these concepts coming out of data science and computation into our statistics curriculum, our students will be better statisticians. So one sort of outlook that I take is that we are not losing by bringing computational concepts into the statistics curriculum. We are gaining by doing that. And yes, there's a struggle between data science and statistics. What's going to happen to statistics? I actually don't really know, but I gotta feel like it's going to be better if we bring more computational problem solving into the way we teach statistics, so our students are much more capable and ready to engage in solving real important problems. So what I want to do now is just walk through very briefly sort of four examples, a few concrete examples of what I've done in trying to integrate computational and statistical thinking into our courses. So the first one is looking at a full case study. The next one is modeling an instructor-student cycle of exploration. Another one is creating a better visualization. And the last one is looking at doing sort of standard statistics from a different perspective, which we call the 3 R's. So here's the case study. And this is data that and at the last day, you're going to get a chance to work on some case studies on your own. This one is one of the case studies. It's food safety in San Francisco. The San Francisco Department of Health visits every restaurant in San Francisco nearly every year, and they score the restaurants. Here's a score of a restaurant is 96 out of 100 for Bamboo Restaurant on Polk Street in San Francisco. And the question is, would you eat here? How do you sort of take that 96 and figure out what that means? Surely 96 is a good number. The Department of Health makes all of their reports public. They're on the web. I've downloaded them, but you can go and get more up-to-date data at any point. And when we download them, we can see that above a 90 is good, and it's typically only a lower risk health and safety violations. And part of the description of the may have high-risk violations, even when you've got a score of 90, right? So might wonder, well, what kinds of violations do these restaurants have? This is sort of an exploration. We can download the data and find that there are 3 data sets. In total, there's a data set that just lists all of the businesses and where they're located in the city. There's a data set which lists every single inspection. Some restaurants are inspected more than once in a year. So there's an inspection per restaurant, or multiple inspections per restaurant. And then there's a data file containing all the violations. So any inspection might result in anywhere from 0 to 10 violations. And so each one of those violations is also is listed separately in this data set. So when we look at that, we see that the raw data is not in a really simple form for us to try and figure out how to analyze. So the business data set has a unique record per restaurant. The inspection one has a unique record per inspection, and there might be some businesses are not inspected in a year, others are inspected multiple times. So it takes a little bit of thinking of, how do I go about combining this? And being able to think about that means you can start to figure out, oh, here's some interesting questions that I might want to answer. To do that, I need to combine my data in certain kinds of ways. So having the skill set to be able to merge data sets with different levels of granularity is something that we'd like our students to be able to do. Then we get to cleaning data. We can look at the differences between the inspection score, the 2 sets of inspection scores, if a restaurant was inspected more than once in a year. And that's the difference. You look at that and you see restaurants don't necessarily improve. We've got zip codes here, and these zip codes are, they've got funky values like California in for a zip code, and you see that there's some amount of data cleaning you might want to do if you needed to analyze anything related to zip codes. So this is part of this full data analysis cycle, as you're starting with data as sort of raw as possible, cleaning it, and then getting to the point where you can analyze it. This is using text manipulation. We've gone in and looked in all of the violations and pulled out things related to cleanliness and related to vermin, and then examined the scores. So we've taken the violation data, matched it with the inspections and with the businesses to figure out which is worse, having an unclean restaurant or some problems with vermin. So it's important for us to see the raw data, to understand the various steps in the processing so that we can do a more interesting or better data analysis. I wanted to give you a few quotes from a survey of data scientists about what they do and about data cleaning. The first quote here says, "I spend more than half of my time integrating, cleansing, transforming data. Most of the time, once you transform the data, the insights can be scarily obvious." Another quote says, "Once you play with the data, you realize you made an assumption that is completely wrong. It's really useful. It's not just a waste of time to use exploration and data cleaning. In practice, it tends not to be just data prep. You are learning about the data at the same time. You're learning about what assumptions you can make." So that's an important part of being a statistician, which we often don't teach our students. And it's really hard to teach because it's this sense of how do you think about the data given you see these particular results as you're analyzing your data. The second example is about keeping a web cache fresh. Don't know if you're aware that when you open up a search engine like Google and you type in a URL or you type in search terms, and then what comes back is a list of possible links to web pages to go and visit. At the time when Google is sort of figuring out which sites to present to you, they're not going around the world looking at websites to sort of figure out what to present to you. They have what's called a cache or a storage of websites from around the world so that they very quickly can return search results to you. Their question is like, how often do I need to update this cache so that you're happy with the results, that they're fresh enough, that they're not stale. And Google went and, this is work with Carrie Grimes, or not me with Carrie Grimes and Ford at Google, carried out an experiment, and I want to briefly describe it to you. They went out and they visited 1,000 websites. They visited them every hour, and they checked to see, had that web page changed from the hour before? And they did that for 30 days, and so they conducted an experiment, if you will, and collected their data and then tried to come up with a procedure for how often should we visit a website. So the data, if you look at this as a sample of what might happen with this might be a particular website that changes at these green dots, these particular times. And when you observe them as at time 1, 2, 3, 4, 5, 6, 7, 8, and you see that at time 1, the website will have changed. That's the green dot between time 0 and time 1. At time 2, you will see that it had changed. At time 3, you see that nothing's changed since the last time you were there. At time 4, you see that it changed, but you don't know that it changed twice. You only know that it changed. At time 5, you see that it changed, but you don't know that it changed 3 times. So this is the data you get, and you're trying to figure out from that data, how do I go and make come up with an algorithm that says, this is how often I should revisit this website. So we can explore the data. So this is this cycle of exploration with our students. We can have them explore it and come up with rug plots. If you're familiar with a rug plot, it's every single time that you observe a change, you make a little tick mark on this axis. And so this is a rug plot for 1, 2, 3, 4, 5, 6, 7 different websites. It's a little hard to see, those green dots, but what do you observe? What kinds of things do you see from this? And you can look at this and then come up with, oh, I have to pay attention to this issue with the data. You can see, what about this one here? Can you see there are a few green dots, but it hardly changed at all? You can see this one here. It changed nearly every time it was visited, but then it didn't go to the full length of time. And this one seems to have changed with sort of quite regular intervals. So that's information that you can then use to figure out how to do the data analysis. Some websites were updated constantly. Some websites were rarely changed, and others didn't make the full 720. That's every hour for 30 days. And you use that information to say, okay, now let's go back and figure out what next to do. So we can talk about the granularity of that data I'm going to skip that one. There we go. We can think about, okay, let's take a look at how often that website changed versus how many times I visited. We come up with another plot that reveals some more information about it. We can look at this. This is on the x-axis, it's the number of visits to a web page. On the y-axis, it's the number of visits where a change was observed. And that's a kind of funky-looking plot. You'd never publish it in a journal, but it is very helpful for us to figure out how to analyze our data. It makes sense, right, that there's nothing up here, right? Because that would be changing more often than it was visited. Here's the 720, and that's the websites that we observed every time we were supposed to. So there are all these other websites that weren't observed the full number of planned times. And so we might say, okay, we're learning from this that let's make sure that we're looking at websites that are similar to each other, that we observed the full amount of time. And so this is what we talked about right before we started the workshop, is there are lots of reasons that we might want to look at subsets. In this case, we would say, okay, I want to look at similar sites that have been observed the sort of right amount of time, and maybe not all the time, but something in between. So we can then come back and say, okay, how might we model these changes? And that's when you can think about probability models like the Poisson process, if this is a more advanced class, and say, all right, let's take a look at simulation studies to see what might happen with that idea that you observe that the website has changed, but not how many times it's been changed. So we could run a simulation study where we simulate the Poisson process, and we have a rate of 4, which is 4 changes per hour, let's say, is the expected, and we observe it for 720 times. What happens by the fact that we only observe it at an hourly interval? So over here is the regular Poisson process, and over here is what you get if you only observe it at regular 1-hour intervals. And you see that it's a very different distribution. It's centered at 1 because it's expected to change 4 times an hour, and so you're seeing a change every time. And so just 1 an hour, 1 change every hour, not 4 changes an hour. So you're getting incorrect information, which sort of says, I'm not going to be able to give a very good estimate if the website's changing so often that I'm not seeing all of the changes. And here's one last picture we can look at. So this says, oh, okay, if I'm changing with regularity, is the Poisson process that I just modeled has this sense of, or has this assumption of homogeneity? Is that held out in my data? So I can look at hour of the day and see if the changes, if it's homogeneous, the changes would be roughly straight across this, follow this line across here. And what do you see? You see definite, look at that, daily changes. And which day of the week do you think is Sunday or Saturday? It's probably these 2 days, right, where people aren't changing their websites as often. So we don't have a homogeneous process here. And then the question becomes, okay, we don't, but if we assumed it, would it be so bad? So this is this balance between you're finding out more about the data, and it's always, the real world is always more complex than our statistical models, but it's good to know the difference between reality and our assumptions. So we might decide that we're still going to proceed with this, even though it's not exactly matching reality. So that's the instructor-student cycle of exploration, where we can discover a lot through simulations and visualizations. The next one is, my apologies, it's very California-centric, and so it might be a little bit hard for you to grasp, but this is about voter registration trends in California. It's a Deconstruct Reconstruct exercise that we do with the students to see the power of visualizations. So I'm going to give this to you. I'll give you a little bit of context, and then I'm going to ask you to come up with some critiques of this visualization. So most of you maybe know that roughly everybody is registered as either a Republican or Democrat in the United States. Those are our 2 main parties. In California, we have counties. You can think of those as like precincts. We have 58 counties in the state. And I think I'm going to leave it at that. And I'm going to say, take a look at this plot and come up with some critiques that you might have for how the plot is made and how you think it should be changed. So I'll give you a minute. You can talk to your neighbor, and then we'll have a discussion about it. So this is the deconstruct phase of a deconstruct reconstruct, and then I'll show you how I've reconstructed it. But I want you to deconstruct it first. Figure out what's going on with the plot, what's wrong with it, what sort of obvious changes you might make, what problems are there, what's the message you think the creator of this plot was trying to get across. All right, what do you think? This is a really terrible plot, right? It's like really bad. I'd like to ask for volunteers. Just one thing you find. There are at least 8 things wrong with this plot or so, but what's one thing that you think is problematic? Yes, in the back. Oh, very good. Is it light green or dark green? Which one's probably Republican and one's Democrat. You might not know in the U.S. that the red color is usually associated with Republican and the blue with Democrat. We've got pale green and dark green. Okay, yes?
I think the x-axis is terrible.
Oops, the x-axis is terrible. Why?
I suppose it's by year. It says by county, but it looks as if it's by year.
Yes.
I can't figure out which year is where. To me, it looks like it's one county.
You can't figure out which year is
across
which,
different years.
right? Yeah, that's a real, like the bars aren't centered on a year. I know, can you figure out if you know when you got to know when our last election was, right? I think it shook the world, maybe? That was 2016. Is like probably right there. Yes, there was somebody, you had your hand raised. Yeah.
And the y-axis, I don't know what they're measuring on the y-axis.
What the heck is the y-axis? I don't know. Yeah? Can you figure it out? You can actually figure it out. It takes a little while to figure it out, but it is figure-outable, if you will. You can see the numbers on the top of each bar, and then you can look over and maybe... I gave you a clue. I gave you a hint when I gave you like 2 pieces of information. What? Yes? Yes. If you add the pair of bars, the numbers on top, they should all add to 58. And remember, I told you there were 58 counties in California, right? So then we can then figure out that the y-axis is number of counties. Not because they told us at all, but because of sort of backward figuring it out. All right. Other issues with a plot that you want to register a complaint about? So what do you think this person who made this plot was trying to say? Looking at trends in voter registration. So what's a key problem aside from labeling and color choices? What's a key problem with looking at trends this way? I'll relate it for what little bit I have learned about South Africa. We're in a province. Is that what you called? My pronunciation's going to be terrible. Gauteng, okay. Which is actually pretty small geographically, right? But has a huge number of people. Right. Okay? And then there are others that are rather large and hardly any people. So what's been counted here? Counties. Okay, so it's, you've heard of LA? There's a Los Angeles County. There's a Los Angeles County. There's a San Francisco County. There are a lot of people who live in those 2 counties. You might not have heard of Yolo County because it's up in the mountains and not many people live there. So what's problematic about a plot that is counting the majority party in a county? Counties aren't voting, people are voting, right? And so this is really hard to see voter trends when we're looking at counties. So in this case, in the Deconstruct Reconstruct, we had to throw the data out entirely and get data that was appropriate to look at voter registration trends. And, okay, the website here is, there we go. Okay, so that's a whole list of problems that you've all pointed out. What's the message? We talked about that, looking at trends. So we went to the California government website and looked at the voter registration counts and produced this plot. What do you see here? So those numbers were for presidential election years, 1992 to 2016. Now my y-axis is something that makes sense. It's percent. In addition to looking at Democrats and Republicans, I added more information. I lumped all the other parties together as other. That's the green. And in California, there's this, you can register to vote without affiliating with a party. And that's called decline to state. So if you look at trends now, you see that decline to state has been increasing. Both Republicans and Democrats have been decreasing, Republicans more than Democrats. So there's a lot more information about voter trends with this kind of plot than the previous one. So that's a Deconstruct Reconstruct. I've given you an exercise to do later this afternoon based on some data from South Africa. Unfortunately, it's not as interesting as this is because it takes a while to find plots this bad that you can then make into something beautiful. So I found a plot that needs to be redone, but it's not quite as interesting what the final result is. Okay, the last one of the 4 topics is constructing a statistical understanding using the computer expressively. George Cobb has a paper published about 10 years ago where he talks about how we need to change the way we teach statistics. He says what we teach is largely the technical machinery of numerical approximations. And in the past, those numerical approximations have come from normal theory. But it's time to recognize that with the computer revolution, we can really change the way we teach. We don't have to rely on normal theory the same way. So I'd like to give you an example using the what's the average family size for families that have college students in our country, or we could say here at the University of Pretoria. What's the average family size for the students who go to school here? So I have a question for you, is if you wanted to answer that, which would be better? A simple random sample of 400 mothers? A simple random sample of 400 students? An administrative data set with 80,000 mothers in it, where those with more children are slightly more likely to be included in the database. 3 possibilities. You're interested in a good estimate of the average family size. What do you think? Is there any one that seems obviously wrong? You know it's a setup, right? I mean, this is right. B is wrong. Why is B wrong? Bias. What kind of bias? Right, there could be, families with a larger number of children are more likely to have someone enrolled at the university, and so it would be a biased sampling procedure. When we're talking about family size, if we have the mother and then get the number of children she's had, then that would be a better estimate for family size. So that would be ruling out B altogether, saying A, or what about C? I really haven't given you enough information to answer. So we will construct an example. Excuse me. So this is about trying to construct, help us figure answers out through simulation. So in the US, there's the current population statistics, and it's looking at the fertility of mothers age 40 to 44. And they have either 1, 2, 3, or 4 plus children. So this is one of these, we're going to simplify the story a little bit. We're going to turn 4 plus into 4. Let's take a simple random sample of this population and do it over and over again. And when we take a simple random sample, we won't get the same number each time. That's what we get. It's a sampling distribution of the sample mean, centered right at our population mean. Okay? So students can learn about sampling distributions through simulation. Here's a question. Professor Meng is a professor at Harvard. He gave a talk at the World Statistics Congress in Brazil a few years ago. I was in the audience. He posed this question. So he had us all vote. It's a trick question, okay? But we can construct something ourselves and try to answer it. The answer here was none of the above, which he didn't include as an option. All right, so let's make an administrative data set of 80,000 mothers where the representation of the mothers is just slightly different than the population. There it is. The gray bars is the true population. The red bars is my administrative data set. You look at those are proportions. They're really close, right? Do you see any differences? There are slightly fewer mothers with one child and slightly more mothers with 4 children. How can this possibly matter? Well, it does. When we look at those, even if we take a sample from our administrative data set or just look at our administrative data set, it's off from the truth. So we will have a much narrower set of possible values, but there's the bias of the administrative data set. Even if it's really small, can be worse than a sample of only 400. So that's a kind of knowledge you can construct by using simulation studies. So data science, now I've gone through these examples. I'd just like to wrap up and tell you about the integration of computational and statistical thinking, which we'll talk about more throughout the workshop. So the philosophy and goals that we're trying to achieve here is that using authentic problems in a scientific context to work with original and raw data, if you will. How do you use a computer expressively to conduct an analysis, to carry out an exploratory data analysis, to construct your understanding of a problem, to create a solution, your solution that is reproducible, for students to have a skill set where they can use data technologies, statistical thinking, computational thinking all together. So the statistical concepts that are not as emphasized in traditional courses that come out here is the basic statistical literacy gets carried out throughout, even for advanced classes, is having a real understanding of variability, data reduction, the method of comparison, graphics, which I think is extremely powerful in the workforce, is not emphasized enough in our teaching. The use of simulation tools to create our understanding of probability models, hypothesis testing, that sort of thing. And model assessment, which we'll talk about later in the workshop as well, in terms of the test train idea and cross-validation. So there are real synergies between statistical and computational thinking that you gain in terms of statistical thinking by including computation in your courses. In particular, if you look at EDA and data wrangling, EDA in the modern era is not about drawing little stem and leaf plots with your pencil. It's about using a computer to create visualizations that reveal what are the next steps that you might want to take in your data analysis. In terms of probability and abstraction and thinking, using simulation studies is a really powerful way to understand what even a random variable is. When you, in a software system such as R, where you can generate a random number, you get to think about, oh, what does that mean when I'm collecting data? What does it mean to have randomness? You can see it happen through simulations. Resampling, modern methods. You can expose students to much more modern statistical methods in terms of, for example, multivariate analysis at an introductory level, if the computer is there to help you do it. And then the idea of reproducibility, communication, collaboration are all augmented by having computational skills. So lastly, what do our students gain by this integration of computational and statistical thinking? Is they get exposed to statistical thinking through another avenue altogether. I'm not saying we should completely throw out mathematics as a way of learning statistics, but to say we should be augmenting it with a different approach, a different environment, which is more constructive. The technical skills students will learn, and they allow them to engage in collaborative problem solving. They will also gain confidence in overcoming computational challenges if we teach them the paradigms behind using our languages, so that they can say, okay, I might not know how to do something in the future, but I know how to think about it and I know how to figure it out. And then the ability to communicate, we know how important that is in statistics, but you can communicate through writing code as well as through writing reports and making visualizations. And that's another skill set that our students gain. And hopefully over the next few days, we'll revisit these things that students gain, and you'll be able to see firsthand. Maybe you'll gain confidence and have an interesting experience visualizing data, and you'll see how you could use that in your classes. So thank you. Let's take a 5-minute break before we move on to the next topic. All right. What we're going to do next is walk through a single case study so you get a sense of how it might be different than what you would use in a traditional statistics class. I want to try and point out the aspects I'll make a list of them as we start and then point them out as we go along as to the kinds of things that we do that are slightly different in this sort of hybrid of computational and statistical thinking. In particular, this case study comes from a class which I, after talking with Franz and Andriette, realized that you might be interested to hear about our new data science major program at UC Berkeley. And so tomorrow I'll spend some time describing it. But one of the core courses in it I've been co-developing and with a computer scientist and co-teaching. And so this case study comes from that course. And I'll point out to you, or maybe it'll be obvious to you as we go through, is how it's slightly different from the way we would teach a regular statistics case study, although it is all common topics that you teach in statistics, but the emphasis might be slightly different. So first of all, what is the data science life cycle? We kind of talked about it already, but the idea is that you start with the context. The context really matters. There's a question that you'd like to answer, but that question needs to be refined to one that you can answer with data that you collect or have been collected. So the first part is understanding the world that you're working in and how to take the general question and refine it to one that you can answer through a statistical analysis. The next part here is the data cleaning, data collection. Also, we'll get to the test-train split. So preparing the data for the data analysis. The third stage here, this modeling, is in this particular case, we're going to look at loss function choices, feature engineering, and model selection. And those are topics that we use in statistics, or techniques that we use in statistics regularly. But some of the language might be a little maybe new to you in terms of feature engineering and that sort of thing. And then we evaluate the model that we build, and that could possibly then send us off in a circle to start the process over again. So notes on the differences by bringing in a more computational data science aspect is that we use visualization, which we've talked about for cleaning the data. We connect regression analysis to the concept of supervised learning. So the supervised versus unsupervised learning, we'll talk about that as well. The idea of the test-train split, which we start way at the beginning before we even carry out EDA. Using a multivariate approach to solving a problem in an introductory course. And looking at a physical model and using that to suggest a statistical model and the difference between the two. Model fitting as an optimization problem. Looking at different loss functions, not all least squares, not all L2 loss. Feature engineering and the interpretability of the coefficients. the difference between inference and prediction in those two worlds, the use of cross-validation in model selection, and how do we assess our models. So those are all slight variants of, or unusual, that to be used in an introductory statistics course. Okay, this problem comes from, I highly recommend this magazine, Significance. This is from a 2014 article where they also published their data, and they went through an entire case study. And I use it in Berkeley, but I thought you guys might appreciate it as well. It's about how do you weigh a donkey in the Kenyan countryside is the sort of general problem. And looking at rural, so the context is in rural Kenya, donkeys are a very important means of transport. If a donkey falls sick, vets need to prescribe the medication. And the dosage depends on the donkey's weight, but the vet can't carry the big scale to weigh the donkey in the rural countryside and needs a technique to be able to estimate the donkey's weight to then figure out what the prescription, the dosage of the medicine should be. So the question is, how can a vet prescribe medication without knowing the weight of the donkey? We can refine that question to, can we accurately estimate the weight of a donkey from other more easily obtained measurements? So you can sort of see the transition in those questions. This is one where you can think about accuracy of an estimate and measurements of the donkey. So here's the design. This was carried out by Kate Milner, a graduate student at the UK. She received a grant from the Donkey Sanctuary to design and a study to answer this question. So two easily obtained measurements from the donkey would be its measuring its girth and measuring its height. These donkeys are brought to the Donkey Sanctuary for deworming regularly, and so it's at that Donkey Sanctuary that they're going to be taking samples of donkeys at the sanctuary that can actually measure the donkey. There will be scales there, so they'll measure its weight, as well as taking its girth and its height. So here's some other design considerations to think about. The donkeys were randomly selected at the deworming site to be included in this study. Why was random selection used? The donkeys were marked after being measured. Why did they bother to mark them? 30 donkeys were weighed twice, with the other donkeys weighed in between them, in between their two measurements. Why bother to weigh donkeys twice, and why bother to have other donkeys measured in between? So these are really nice statistics questions about the data design, which are important questions when it comes to thinking about how generalizable our results might be. So they were randomly selected to avoid selection bias, right? And they were marked to make sure that they were not measured more than once. And they wanted to weigh some donkeys twice to see how accurately their scale is. And they had other donkeys in between so as to not impact the person making the measurements, so they wouldn't know that they were weighing that same donkey twice. Okay, here's the data. Here are the variables that were collected on them. Their BCS stands for their body condition score. 1 is emaciated. It goes up in half scales to 5 is obese. Their age is also measured in categories. Their sex is stallion, gelding, or female. Their length is measured in centimeters, their girth in centimeters, and their height in centimeters. And then their weight, and that's the response. That's the thing that we were trying to predict when they go into the field by using some of these variables. So in terms of data cleaning, we could first look at the 30 donkeys that were measured twice. We can take their first measurement and their second measurement, look at the difference, and see how much they differ. So this is a histogram of the differences. So we can see that their difference is either 0, so they were exactly the same, -1 or +1. So if we back up and we say, well, so does that matter? And we look at the weights of the donkeys And you see there are 77, 174, 116. So a difference of 1 is telling us essentially that we have quite an accurate measurement, and we don't need to measure the donkeys multiple times, which we might have wanted to do if the measurements were a little bit all over the place. Okay. Further data cleaning is we look through and find that one donkey has a body condition score of 1, and only one donkey has that. One has one of 4.5, and there are no 5s, so that's the heaviest donkey. And one donkey weighs 27 kilograms and is determined to be a baby. So what do we do with these 3 donkeys? In this case, we can decide to take them out of our study. So this is subsetting again. We want to subset our set of donkeys to not include the single emaciated one, the single obese one, or the baby, and say that when we're thinking about how generalizable our results are going to be, they're going to be for healthy donkeys that are adult. And so we're eliminating those 3. And now we're to the modeling phase. So here's where we talk about supervised learning. That's when we have labeled data, and we want to make predictions using, so in the future we won't know what the labels are, and we want to make predictions for the labels. Here a label is the response, is the weight of the donkey. And so we have all of these various measurements. We're going to build a model where we've got supervised data where we know the donkey's weight, and we're going to use it in the future in places where we don't know the donkey's weight. Test train split comes in at this point, where we're going to split the data before we do any real EDA into a test set and a train set. I want to just briefly show you why we do that. So let me back up and say the test set is going to be set aside, and we're not going to look at it until the very end after we've built our model. The train set, so again, we're splitting our data set into 2 subsets. The training set we're going to use to build a really good model. And then in the end, we're going to evaluate our model on the test set. So why do we want to bother to do this? Here's just a simple example where we've got data, and we could fit various models. So we could fit a straight line to it. That's the purple line. We could fit a sine curve. That's the red curve. We could fit something it's wild all over the place, but gets really close to a lot of points. So how do we choose between these? If we looked simply at how close does this model fit my training data, the best one is the squiggly one that goes all over the place, because it's going through nearly all the data points. And so if we look at the root mean square error, the size of the error, for just my training set for these various models, the worst one's the basic simple linear model. The best one is a really fancy 50 variable equivalent. So we'd say, let's go with that one. It's got the smallest error. It does the best job. But now we bring in our test set, and we say, okay, how well does that do? It does an impressively bad job, because it did a really good job of fitting our training set. And when we have data that's slightly different, we have huge errors. And you see the difference between the other 3 models, they were nearly equivalent. And when we look at that, we say, well, let's go with the simplest model. We always go with the simplest model, right? All right, so that's the idea behind the test train split, is to avoid sort of fishing or overfitting. And so the general idea is that your training area error decreases as the complexity of your model increases, but your test error decreases and then starts to go up as you have more complex models that basically overfit your data. You've got sort of a best fit, you can underfit and overfit. So we're going to do this test train split. We have our data set. We take a certain portion aside, set it aside, and wait until we've done all of our work to then use it to evaluate how well we've really done. How do we make this split? Randomly. If the data are in time or there's geography, we might need to incorporate that. It depends on the particular problem. often. We do it at random. What's a good test train split? 90-10 is one. Others are, if you've got more complex models, you might want to have a larger test set. Okay. So we're splitting our data in an 80-20 split. We set aside 20%. Now we're going to do our EDA on the 80%, not all of the data. And we're going to build our model on our 80%. So here's just a little bit of mathematics as to what's going on here. We optimize our model on the training set. So here we've got our training data, our response, which is our weight. Here are all of our covariates. That could be the length, the girth, etc., and the parameters for our model. And we minimize this, and that gives us our estimate for our parameters based on the training data. Then when we want to evaluate how good our model is, we've picked our best, what we think of as our best model, then enters the test set. And we have our weights for the donkeys in our test set and our covariates for that test set, but we're using our parameters from our training set. And that tells us how good we are at making predictions from the model that we've built. Any questions on that? Okay, let's now go to EDA. So we start making some plots. Here's a box plots of the body condition versus the weight, and a box plot of age versus the weight. Okay, when you look at those, is there anything comes to mind that might inform you as to how to build your model? What do you think on BCS? Is there a linear relationship between BCS and weight? I think I see a little curvature. What about age? What do you see here? Looks like by the time the donkey is is 10 years old that there's no relationship. So things to keep in mind. Sorry, I'm going the wrong way. There we go. Nonlinear, and here's two more plots by sex and weight. Looks like possibly there's not a big difference by the sexes. This is girth and length. They're highly associated, so these are covariates. That makes sense. The bigger around, the more likely the donkey's longer. So there's not a big difference between the stallions and the females, and girth and length are highly correlated. So we can use all of that when we're trying to figure out our model. So now that's a starting point for building our model. We might, at this point, start with a physical model to think about a donkey as just a cylinder. And so we can take its length and its girth and then use that formula to come up with a model that we might want to start with. In this case, we could say that some function of the weight is some linear function of girth and length. Maybe this should be the log of weight is some kind of function of girth and length. We can consider various models. Here's something that we don't usually do in statistics is we talk about possibly having a different loss function. So maybe not using least squares. They had two different scenarios when you need to administer an antibiotic or an anesthetic. With an antibiotic, the effect is less sensitive to the weight of the donkey, and since you don't want the donkey to get reinfected again, it's better to overdose it than underdose. So it's better to possibly overestimate the weight and overdose the donkey, and it won't hurt the donkey. On the other hand, for an anesthetic, the effect is much more sensitive to the weight of the donkey. You want to be careful to not overdose the donkey. It's better to underdose it, and if it's not effective, then to give it a little more. So what's the impact of that is that we can look, sorry, I've got to get used to this, going in the other direction. We can look at the difference between the actual and the predicted as a percentage of the predicted. And this is a loss function that's kind of it is quadratic, but it's not symmetric. So a question, does a negative value correspond to an overdose or an underdose? It means your prediction is too high, so you've overdosed. And Does it make sense that this would be sharper, steeper? Because you want to penalize overdosing. Right? So here's a loss function that, so now you're thinking a little bit more about loss functions than you might be when you're just running a regular regression. And so on to feature engineering, which is what our computer science colleagues call variable selection. The process of transforming variables or selecting variables. Feature engineering, you can encode qualitative data, non-numeric features into something that you can use in your model. You capture domain knowledge, and you can transform complex relationships into simple linear ones by possible, like our physical model, where we're taking logs and things like that. So some basic transformations. We have categorical features. I wanted to focus on that for a minute. So how do we convert this into meaningful values? We have female as 1, geldings 2, stallions 3. What do we do with that? How do we use that information? Do we use it as 1, 2, 3? This is where we typically instead create dummy variables, and we'll talk about that in a second. We could use box-Cox transformations to select the transformation. Here's an example of using it to look at the various models with all 3 variables versus some subset of 2 of them. Is trying to minimize the prediction and choosing the transformation that minimizes the prediction. And we see the minimum is roughly around 1/2, saying square root. Here's the log transformation. So it gives us information. We don't have to go exactly with that, the minimum, but it can help us choose between, here we go, I'll go back. When we look at this, do we want to use a 3-variable model or a 2-variable model? In which case, which 2? Do we want to use a square root transformation or a log transformation? And so we see here that the 3-variable model is not much better than the 2-variable model of girth and length. So we always go for something that's simpler, and oftentimes a log is considered simpler than a square root as well. So let's take stock of where we've been. We dropped 3 records. We divided the data into a 20-80 split. We used EDA to show that some of the categorical variables could be useful in our model. We selected a loss function, and we examined a model based on 2 variables, and we went for the square root transformation. Now on to categorical data. We can think about what do we do with it. We saw in this case that we probably don't want to bother with sex. But we can create, it's called in the computer science world, one-hot encoding. We call it dummy variables or indicator variables, where for every different category, we take, these are records along the side. The first is a gelding. It becomes a 1, and all the others are 0. Stallion is 1 here, and the others are 0. The female, 0, 0, 1. And we can now use these dummy variables. Why would we want to use dummy variables in this case? And that's, we can make pictures of when we include a dummy variable, that's allowing our model to have a different slope if we're fitting a linear model. There's also the BCS is a number, so why not just fit it as a number? Because a number, the difference from 1.5 to 2, all you know is that 2's healthier than 1.5, but that half-point difference from 2 to 2.5 is not necessarily the same as 1.5 to 2. So when we think back of our box plots, we might want to, in fact, collapse some of these, but we definitely want to treat it as categorical data. Now there's our box plots for BCS. I guess I did not collapse it, but it allows us to not be fitting some kind of curve to that number. And then here we'll want to collapse categories with age. Okay, so we've now gone through our sort of studying what kinds of transformations that we want to make with our data. And we're now at this sort of difference between inference and prediction. In the prediction world, we care about we're going to estimate the weight of a donkey, and I want it to not be far off. In the inference world, I'm building a model that explains the weight of the donkey as a function of its girth and its length, and I care about what those coefficients are. So do you know, are we in both of those worlds? I think we're in both of those worlds. The vet is going to use our model. So here's another example of where the difference is between the computer science approach to the statistical approach. We're often really focused over here on inference and rarely look over here at prediction, whereas the computer scientists are often really focused in prediction and they don't care at all about inference. They don't care what the variables are in their model, oftentimes. So we care about this because we want to know, we want to be using variables that the vet can easily use out in the field, but we also want to make sure that we have good predictions. So how do we go about actually picking our model now is we take this test train idea and we use the idea of cross-validation to then mimic the test train paradigm. So remember, we took our data and we split it into a test set, we split it into a test set, which we set aside, and now we're doing all of our analysis on the train set. And we want to pick something that's good, so why not use this model of evaluating on a test set within our training set? And that's what we do, is we do what is called V-fold cross-validation, where we take a little bit of our training set and set it aside and build our model on what's left. Then we take a different set. This is 5-fold cross-validation. We set it aside and build our model. And we do that for 1/5 of our data, each time having a set we put aside and a set we build our model on, put that all together and use that to pick our model. So we're imitating the test train paradigm on our training set. So the mathematics of it looks like this, where we have a fold is our test set, and we are evaluating it on the model we fit with everything else that was in our training set except for that fold. And we do that 5 times over and put it all together and use that to pick our model. Okay, so we use this to pick our model. Our final model assessment. So we've picked our model, and we now bring back our test set, our original one that we set aside, and we compare how our model does with this new or unseen data. And we look at the difference between the predicted weight and the actual weight. And we find that nearly all, 95% of the actual weights are within 10% of the predicted weights. So we've done a pretty good job with a very simple model. And so that's a case study from start to finish. And we went through this entire cycle, and hopefully you see how we're actually using some somewhat sophisticated concepts that maybe we typically don't show to students until they're in their master's studies, but that we can do it from if we're looking at it from a computational perspective, we can incorporate more sophisticated ideas, and the students can understand what's going on and know how to use things in the future when they're trying to do their own case studies. So it's now time for lunch, but are there any questions about this little case study? Yes, what if the donkey weighs less because it's sick? So there's 2 things going on. Let me say this. We can look at the donkey that weighs 27 kilograms and look at its other measurements. It's also, its length and its girth and its height are also really small. It's a good point. If we looked at the histogram of girth and height, that donkey is way out there as an outlier. So it's not just that it weighs less, it's also much smaller. And so whenever we have situations with an anomalous observation, we want to be, sometimes you do want to include it when you want to say, yep, that's, or you want to do a whole separate study for smaller donkeys if it's a different breed, and you can identify these are two different types of donkeys. You might want to fit two entirely different models. In this case, it's just one donkey, and we don't want that donkey to impact the model that we're fitting for all the rest of them. Yeah?
2 slides back to slide 12, which is donkey number 8.
Okay. Oh, I'm sorry. Where do you want me to go?
Slide back to slide 12.
Slide 12. Okay. Oh, can we see him? There he is. To make the point. Is that what you're saying? Yes. Yes. So now we see it. Here's that. Here's a donkey, 27 kilograms. You look at its height is 70 compared to all the others, which are above 90. 66 is its girth. All the other girths are 90 to 110. And 46 is its length, and all the others are around 80 to 90. So it's a different animal. We can conclude. Well, let's say this. We can conclude that donkey is really different than all the rest. Okay. The significance article tells us that donkey's a baby, but you're right. This is where context, I'm just taking that from the significance article. We can conclude that donkey's really different from the rest. Yeah. Any other questions? Oh, yes. So in particular, it's the uncertainty in, let's say, the coefficients. You also have uncertainty in terms of prediction as well, but that's you're distinguishing between those two kinds, I believe, right? And I wanted to add, I forgot to mention this when we got to the one-hot encoding. It's kind of related to what you're saying, is that, so I co-teach this class for the computer scientists, and we're always after class saying, so why did you do that? This is what I would have done. And in the case where we talked about when we are going to build our model, with the dummy variables, we don't want to over-parameterize our model. And why we don't want to is because we want, exactly in this inferential side, we want to look at the coefficients and be able to interpret them. So when the vet goes to the field, she'll say, oh, I see that this donkey is this falls into this age category. So when I'm going to predict its weight, I'm going to add this amount to it. Whereas in the prediction world, the black box world, let's say, the computer scientist said, I don't care if it's over-parameterized, because when I do my regularization, it's all going to work out in the end. But that's because they don't care about all of the coefficients, and we do. They're only caring about the prediction, which would be the same whether you're over-parameterized or not. Where it's important to also be able, for us, to say, we want that vet to be able to go and say, okay, this is the girth, this is the length, it falls into this age category, it has this BCS, and therefore I can come up with my estimate for, or my prediction for its weight. They're not going out into the field with a computer that's got the sort of model, the black box model in it where they punch it in and out comes a weight. Right? And you're absolutely right. There's value in inference. What's happening at Berkeley now in terms of research is that there's been a bit of a pushback on the sort of black box machine learning approach. And there are several researchers in my department who are looking at issues of interpretability and causality in the world of machine learning, and how do we sort of pull things back a little bit and think a little bit harder about how we're using this like really powerful, machine learning approach and what's coming out. And there's a lot of politics that surround that as well. You have to be careful with the models that you're making predictions for if you don't really understand how certain back. Is that what you said?
No, I'm saying before somebody would come to this
far, they must have gone through some sort of statistical, like theory. Would you think
they
that
don't have to.
They don't have to.
I think the beauty of some of this stuff. Well, I'll say that what I described here is used at an intermediate level class. Yes. However, some of these concepts we use in our introductory class, and the idea of test-train splits, you want to bring that in sort of early on because it's about, can I generalize what I've done to a bigger world? And the test-train split idea is exactly about that. Fitting that loss function with all those dummy variables, that's a more advanced topic. So some of these concepts can be used at an introductory level, and others might be a little more advanced. Yeah, right. All right, that's it. So coming up this afternoon, we're going to get more involved in graphics, and you'll have a chance to use R as well. So I'll see you after lunch.